Alright, I've got a whole bunch of problems to do today, so my computer is probably going to catch on fire. But anyways, until that happens, let's keep going with this problem. So, we want to prove that's a norm. So this is just a whole bunch of stuff that we have to check, and it's all pretty straightforward. But we still have to do it. So for the triangle inequality, let x and y be an x. By the way, typically these things, like even though like they are pretty straightforward, it's still like sometimes when you actually write out the details, you'll find out, oh, these things aren't quite as easy as I thought. So since this is a basis, we can write x and y as linear combinations of the basis elements, and aj's and bj's are going to be constants. So then x plus y, 1. Well, if we just write out what x plus y is, it's just the sum from 1 to n, and we can collect like terms or whatever you want to call it, and you get this, but then by definition, this is just, absolute value, aj plus bj, and then we just use the triangle inequality. A lot of these things, in fact, when you're trying to check something as a norm, you basically, it's typically something that's in terms of another norm, and so you basically typically end up going to whatever other norm you know things about and use the triangle inequality from that norm to get a result for the new norm. So anyways, you just write this out and it just becomes x1 plus y1, and so we have the triangle inequality. For scalars, remember we gotta be able to bring scalars out. So if you have lambda, a scalar in k, then let's see, lambda x1, this is just, so you can factor out the lambda, this is aj, ej1, so this is, right, we want to bring the lambda inside. And this is equal to, by definition, lambda aj's, but now we can bring this lambda outside. All these sums, by the way, are a sum from j equals 1 to n. So this, by definition, is just the aj ej, and that's lambda times x1. So there we go. And certainly if x equals 0, then aj equals 0 for all j. So norm of x1 equals the sum from 1 to n of aj, which is just the sum of 0 a bunch of times, which is 0. So that proves it's a semi-norm, and to prove that's a norm, we want to say that if x is not equal to 0, then there must exist some am which is not equal to 0, where m is one of the indices between 1 and n. So norm of x1 is equal to the sum from 1 to n of aj, and that's certainly going to be greater than or equal to just the particular am, and this we know is strictly greater than 0. So in particular, norm of x1 is not equal to 0. Hence, well, I shouldn't say the norm of x1, I should say this thing of x is not equal to 0. So hence, this is a norm. So now that we know it's a norm, we could call it a norm. But before that, we didn't know it was a norm. So you can't call it a norm if it's not necessarily a norm. When you know it's a norm, it's a norm. Okay, and now we want to prove part B. So I'm going to scroll down a little bit, and hopefully we remember what part B is. So we want to prove that, I just forgot. we want to prove that this map is continuous, where we take something in Kn and put it in this space X. So let's do that. Part B, let T of A1, we'll call it T of A, it's T A1 through AN equals sum from 1 to n AJ EJ. To prove T is continuous, it suffices to prove T is linear and bounded. Was linear one of the things we wanted to prove? No, I guess it wasn't. Oh, but if it's we know that bounded linear, we know that for linear functionals, bounded and continuous are equivalent. So we do need the linear in order to have the equivalence between bounded and continuous. So linearity is obvious. And that's a little bit of an annoying phrase because really, like, in terms of writing, like, if something's obvious, there's no reason to say it. But basically, when I say linearity is obvious, I mean if you try, if you have enough experience with these types of problems, then the first thing that pops into your head to try to do should work. Maybe the second thing. That's similarly to saying that something is trivial. It doesn't mean that it's easy to do. It just means that probably the first or maybe the second idea that comes to your mind to use will work. So basically here, linearity of T will come from linearity of these sums. And so you can work out the details, or you can just leave it at this. As for boundedness, suppose norm of A equals 1. And this is in Kn, i.e. this norm is in Kn. This is a norm on Kn. So what does that mean? Well, really, the Euclidean norm on Kn is just this, the square root of this is 1. So, sum from 1 to n of aj squared equals 1, because 1 squared is 1. So then, for all j, and this is of course j between 1 to n, but I'm not going to write that out, aj in norm is less than or equal to 1, because otherwise this sum can't equal 1. It would end up being greater than 1. So anyways, therefore, the norm of dA1 is equal to the sum from 1 to n of aj ej1 by definition, and this again by definition is 1 to n aj, but each of the aj's we know are bounded by 1, and this is n. So T is less than or equal to n because it's a supremum over all such it's a supremum over all such 1 norms of TA where norm of A is 1. Euclidean norm of A is 1. So this is less than or equal to n, which is a finite number. So T is bounded and thus continuous. Right? So that's that. Now we want to prove another thing. we want to prove that this set, the set of all x and x, such that the one norm of x is 1 is compact in the topology on the one thing. So here, let's put that there. So let's do part C. So let K be the set of all A in Kn, such that the sum from 1 to n of Aj, Ej is equal to 1. And of course, A is equal to the vector A1 through An. So then, what is Tk? Tk is all those elements x and x, such that norm of x1 is 1, right? Because T sends each A to its linear combination with the EJs. And so if you have an x and x such that the norm of x is 1, then that means the one norm of x is 1, that means precisely that the sum of the AJ, the norm AJs, is 1. And that means that A is in... Yeah, and that means that A in Kn is such that this thing is equal to 1. Yeah, this is clear because everything in here is just of the form TA. Okay, so this Tk is this. So we want to prove Tk is compact, right? Because Tk is precisely this set that we're asked to prove is compact. Since here, by part B, T is continuous, and so it suffices to prove that K is compact, because it's a standard topology fact that continuous functions map compact sets to compact sets. And so let's see here. Yeah, and so now you see why I called it K, because it's going to be compact. So let's see here. Norms are continuous, and K is defined by a closed condition with respect to the one norm, and so K is closed. Next, for every single A in K, we know that the sum from 1 to n of Aj, Ej, 1 is equal to sum from 1 to n of Aj equals 1. So each particular Aj is less than or equal to 1. And so sum 1 to n of Aj squared is less than or equal to the sum from 1 to n of 1, which is equal to n. So let's see here. So the norm of A, I'm going to say the norm of A in Kn for the Euclidean norm is less than or equal to square root n, because you just take square roots on both sides. I guess that's not necessary, but the point is K is closed and bounded in Kn, so K is compact. Oh, where'd it go? I think I accidentally erased all of it. So K is compact, so Tk is. And that's just closed and bounded and k to the n is compact. That's just a standard analysis fact. There's a name for that. It's like two important guys in analysis put their name on it, or at least some people put their names on it, but I forget what it is right now. Is it Heine Burrell or I don't know. Bolzano? I don't know. I'm not going to try to guess it because I'm going to get it wrong, likely. Okay, so that's part C. So now, what do we want now? Jesus, this is a long problem. All norms on X are equivalent. Okay, so basically, so we're going to take a norm on X, and if it's equivalent to the one norm, then that means that all norms are equivalent to the one norm, and so all norms are equivalent. So let's go down here and prove this. So part D. So we're going to let this be any norm on X. Let X be a linear combination of AJs in X. Then the sum from 1 to n of AJ, EJ with respect to this whatever norm we were given, it's certainly going to be less than or equal to 1n AJ. Because if you you could just bring the norms inside and bring the scalars out, and you're going to get this. And this is certainly going to be less than or equal to, we don't know what value this is going to put on the norms, on the EJs, but it's certainly going to be less than the max overall J from 1 to n of EJ times the sum from 1 to n of the norm of AJ. And this is just the max for all J of EJ times the sum from 1 to n of AJ, EJ, one norm. And so we have an inequality. Okay, so there exists a C such that this miscellaneous norm is less than or equal to C times the one norm, where C is some constant. And so this is half of what we want. What we want is we want another constant like this. And so that's what we're going to do now. So for the other inequality, note that this norm is continuous because all norms are continuous. Norms on nice spaces are continuous. So, so this norm is continuous. Blah, blah. Where are we? Okay, so let K. Oh, I wonder what kind of set this is going to be x and x such that norm of x1 equals 1. Oh, this set. So by part C, K is compact. So this attains its minimum at some, let's call it lowercase k and uppercase k, because those look dissimilar enough that they will never ever cause any confusion. Now 0 is not in k, so k is not equal to 0. Again, capital, not capital. So the norm of k is strictly greater than 0. Then for all x in the set non-zero elements of x, the norm of x equals norm of x1. I guess you have to prove, like if you want to be really pedantic and annoying, you have to prove that x is not the zero space in order for this to exist. If X is the 0 space with just containing 0, then all norms are equivalent because, I mean, it's just one point, and it can't not be the case that all norms are continuous. But also, more importantly, no one cares because that's a boring space. So, or at least I don't care. So, for all these and these, norm of x equals norm x1 times, we're basically just multiply and divide by the norm of x1 and use a linearity here. And then this will be greater than or equal to, well, this x1 stays. And this x over x1, this is an element of the one norm of x over norm of x1 is 1. And so the norm of this is going to be greater than or equal to the minimum value that this norm attains in K. Because this is in K, so this is going to be less than or equal to this times small k. And this inequality holds trivially if x... Oh, yeah, I guess we should write that. This inequality... Oh, there we go. This inequality holds trivially if x equals 0. So I guess it's fine if x has this 0.0. So, that was weird. Hence, okay. Thus, there exists a C such that C norm x1 is less than or equal to x. So C norm x1 less than or equal to norm less than or equal to C x1. Therefore, this is equivalent to the one norm, and hence all norms are equivalent. And there you go. It's a little bit of a long proof, but now we have finished it.